Hello, everyone, and welcome back. Today, we are going to be starting our second case study of the quarter, where we're going to be exploring classification. And so in this pre-lecture video, I'm going to be introducing some of the terminology behind this kind of new area of study in machine learning called classification, and I'll be introducing the context of what we're going to be kind of studying in this case study. Before I introduce that, I want to kind of give us a quick recap of what we've learned so far. So for the past 2 weeks, we've been working on housing prices with regression. So regression is the case where you're using machine learning to make predictions where the outputs or the targets that you're trying to predict are real numbers, like a price. And so we really focused on house prices, but regression is so much more general than that. It works at any time you're trying to model a number. So we talked about what is the regression model, how to assess the performance of the model using a test set and also a validation set, to choose the right model complexity when you have many possible model complexities to choose from. And we talked about how model complexity can feed into types of errors like bias or variance, and how both of those can contribute to the future error your model might receive. And then last week, we started talking about regularization. So we were into the world of how can I change my quality metric in my regression model so I can hopefully prevent it from overfitting or steer it away from overfitting. And we saw that by adding a term to our quality metric that measured a notion of overfitting, which usually is just measuring coefficient magnitudes, we saw that we could either get ridge regression or lasso, depending on whether or not we use the L1 norm or the L2. So for ridge, we use L2 norm. And for lasso, we use the L1 norm. Remember, L2 norm we denote as this kind of W within these norm bars, and then we use subscript superscript 2 to represent the 2 norm. And as a reminder, this is the sum from J equals D of Wj squared. And we also talked about the L1 norm, which is denoted with this norm notation with just subscript 1. And then it's the sum from J equals 1 to D of the absolute value of Wj. And we saw that both of these, if we use them as regularizers, lead to different properties of the learned predictor. For ridge, it makes all the coefficients small if you make lambda larger. And for lasso, it does the same, but it tends to make sparse predictors, meaning that most of the coefficients tend to be 0, or more of the coefficients tend to be 0, whereas ridge just tended to be close to 0. That had to do with the geometry of those regularizer terms. Now, we don't need to worry too much about that geometry argument. You just need to remember that lasso favors sparse solutions with sufficiently large lambda. And we talked about how you could use that as one potential tool for feature selection. So that was kind of the world of regression. There's lots of other things you could do with regression, and we'll see more later. But those ideas and techniques, talking about residual sum of squares or talking about bias and variance or regularization, those are key ideas that we'll use in lots of different aspects of this course. And we'll also see that further ideas in this course have applications in regression. So we're not going to be completely done with regression, but now we're going to change gears slightly and talk about a different application in this field of classification. So classification is when you're making predictions about discrete values. What I mean by that is when you're trying to make a prediction on whether something like a restaurant review is positive or negative. Did the person like the restaurant that they're reviewing, or did they hate it? This is just one example, and the example we'll be focusing on in our case study. But classification is so much more general than just predicting whether or not someone liked or didn't like a restaurant. Let me show you some examples of this. So one example that you probably use in your day-to-day life is spam filtering. And you might not realize you're using it because most modern email services come with it. So usually you have a bunch of emails being sent to you all the time that get automatically filtered to your spam folder. And sometimes it makes mistakes, sometimes it doesn't, but it usually does a fairly good job at finding emails that are blatantly just ads or trying to fish for your information or anything that's just not relevant and sending it away. So if we're going to model this as a machine learning task, we might use something like information about the email as inputs, like the text of the email, and we'll talk about how to represent text. Maybe the sender, the subject, what time it was sent, and lots of other things. And then the output here would be a label, either spam or not spam, which we sometimes call ham. So instead of predicting a number like a price, we might want to predict a label, which takes on discrete values, spam or not spam. And again, we're going to commonly refer to this as ham when it's a good email. I don't quite know where that terminology comes from. As a vegetarian, I don't quite get it. I don't think ham is a particularly good thing, but we'll consider ham being not spam. This task is a particular type of classification problem, where you're trying to classify an email rather than trying to predict a price or a number about it. And in this particular example, where you have two options, spam or not spam, we call this an example of a binary classification task. And what I mean by that, by binary, when we use the word binary, does not necessarily mean zeros or ones. It means two options. And in the world of computers, that's always 0, 1. But this is a much more general term when you have one of two options. This is not the only type of classification you might be concerned about. There's also a very natural extension to this, which we call multi-class classification. When the classes you're trying to predict, classification. When the classes you're trying to predict might be more than just two possibilities, where in this case you might have a picture of something like a dog, and you might want to output kind of what labels from a set of many possible labels you think are relevant for this picture. So you might say, like, you most likely think it's a Labrador Retriever, maybe next most likely is a Golden Retriever. We'll talk about outputting likelihoods as well to say how confident something is. But in this case, a picture might belong to more than one label, or there might be more than two labels that might be possible. And so we call this a multi-class classification problem. So we're going to see lots of different examples of classification. For the most part, to start off with, we're just going to focus on the binary case, and everything we'll talk about extends quite naturally to the multi-class classification. So what I'm going to start us off with is we're going to talk about our ML pipeline. We have training data, we have feature extraction, an ML model, a quality metric, and an ML algorithm. A lot of these things may or may not need to change from our regression setup. I'll start with right now, there's nothing necessarily you need to change about your training data or feature extraction. In this one example where we're working with text data, we'll have to do something a little bit clever with our feature extraction, which we'll come back to later. But right now, I'm just going to introduce a type of model that you might use for classification. And then in class today, I'll talk about a quality metric or many quality metrics you might use to assess the quality of your model or the learn predictor from. So what we're going to be focusing on right now is a sentiment classifier. So we want to take a sentence from a review about a restaurant, feed it to a predictor that we've learned following some model, and we want that predictor to output positive or negative. Where positive is it's a good review, they had a positive experience, and negative being they had a bad review or they had a negative experience. And we'll use, in this case, when we have a positive label, we're going to use the prediction for the point, y hat of I, to be +1. And then if it's a negative review, a negative experience, we'll say our y hat of I is -1. Saying it's a negative root. You might be wondering, wait, Hunter, didn't you just say with classification we don't worry about numbers? Well, it's very common to just represent your label as a number, but you're not treating it like a price where it could be any number between 0 and 2 million or something like that. It's only discrete options, -1 or +1. It's just convenient to write those down as numbers so we don't have to write out positive and negative every single time. So this is the idea of the model. It takes its input, or it takes its input features, and then it makes a prediction, either +1 for positive or -1 for negative. So let's try a first idea of how to represent this model, an idea for what a model could follow in order to make these predictions. So here's the idea. Make a list of good words and a list of bad words, and then classify a sentence by whichever type appears more frequently. So somehow go on the internet and find a list of positive words and a list of negative words. So positive words might be things like great, awesome, good, amazing. Negative words might be bad, terrible, disgusting, sucks, and so many others. And then you can imagine this first implementation we'll use, we'll call this the simple threshold classifier, takes a sentence from the review and then just counts the number of words that are positive according to this list of positive words, counts the number of words that are negative according to this list of negative words, and then if the number of positive words is greater than the negative words, then report +1, otherwise report -1. So just for a concrete example, if the number of positive words was 3 and the number of negative words was 1, then we would predict +1. So here's an example of this. Sushi was great. The food was awesome, but the service was terrible. Oh, sorry, that should have actually been great, awesome. And we'd probably say that on average, or most likely, this is a more positive review because it had more positive outcomes or more positive words associated with it. There are some pretty clear problems with this approach, namely, where do you get this list of positive and negative words? Who determines what words are positive, what words are negative? That sounds like a whole machine learning problem on its own. And different words have different degrees of sentiment. What I mean by that is great seems more powerful than good, and something like was kind of bad is not as bad as it was terrible. So this doesn't necessarily quantify this notion of degree of sentiment. So how can we weight these things differently? Now, there's another problem with this approach that I just described, is that sometimes single words aren't good enough for capturing meaning. So if you have something that says good, that generally means positive, but not good is a negative phrase. But if we used our simple threshold classifier on this and looked at not good, we'd count it as a positive phrase because it had good in it. There are ways around this. What we'll focus on in this class is we will use machine learning to identify which words are positive and negative, and maybe get an estimate of their degree of that sentiment. So looking into how to identify that great seems to carry more weight than good. This second problem that I pointed out, which is like this one word might not be good enough. One way around this is using more complex features. What I mean by that is that in this example I was showing before, we were looking at one word at a time, which we call a unigram model. Meaning one. Gram is a fancy word from the natural language processing community, but we're looking at one word at a time. One way of getting around this, like one word's not enough, is to use more complex features by maybe looking at two words at a time. They call this a bigram model. We are not going to talk too much about this idea of unigrams for words, bigrams for words. This is something that's squarely in the space of natural language processing, which uses machine learning techniques quite frequently to do their analysis. But we aren't going to talk too much about how to represent human speech because even this unigram versus bigram thing is relatively complex. And there's so much more that goes into how do you understand natural human speech patterns that we just aren't able to dive into. So we're not going to focus too much on a lot of weird cases that can come up with human English. We're going to really focus on this first kind of two problems I highlighted, which are learning classifiers from data to associate positive or negative sentiment. We're not going to worry about too much linguistic definitions here, even though those are very important and very crucial for natural language processing. We're not going to really focus on this last problem. Okay, so here's my idea for kind of a slightly better version of this classifier. My idea is use labeled training data to learn weights for each word, and then use weights to score a sentence. What I mean by that is let's gather a bunch of reviews that say the sushi was great, the food was awesome, the service was terrible, and we'll have, hopefully, someone go through and tell us, was that a positive or negative review? We'll need a human to tell us whether something was positive or negative. And then we'll gather lots and lots of data of example sentences and example labels, and then somehow learn a model from that labeled data that tells us for each word, is it more likely to be a positive sentence or more likely to be a negative sentence? We'll get back to later on how to learn these weights. That good seems to have a weight of 1.0. Great seems to have a weight of 1.5. We're not going to focus on that today. We'll pick that up on Wednesday. So right now, just pretend with me that I have a magical ML algorithm that takes a bunch of this labeled text and learns weights that associate how positive or negative a word is overall and towards the prediction. So good might have a weight of 1. Great might have a weight of 1.5, showing that it's also a positive word, but has more strength than good. And then you can imagine the same relationship with bad being -1. It makes it more negative, and terrible being something like -2.1. Again, the specifics of how to learn those weights we'll get back to, I promise. Let's just pretend someone magical ML algorithm told us these weights, and we'll use them. And then we'll come back to how do we learn them with machine learning. So how might I use these weights, assuming I have them? Well, I can use them to get a weighted average of the positivity of a sentence. So what I can do is come up with some new kind of score function. So when xi is the sentence, sushi was great, the food was awesome, but the service was terrible, I can come up with a score that goes and looks up all of the words in this sentence in my table and adds up the weights for each time that word appears. So what I mean by that is the word great appears once, so we'll take the weight for great, 5.1, and multiply that by 1. The word awesome appears once, the weight for awesome is 2.7, so we'll add on to that score 2.7 times 1. If awesome appeared in this thing twice, we would multiply 2.7 by 2. So we just count every time the word appears, multiply by its weight. But then also there's the word terrible in this review. And so with the word terrible, that has a negative coefficient, so we'll subtract off 2.1 times 1. And then we add all of these numbers up, and we end up with an overall score of 2.1. And that's what we're going to say is the score of this sentence. We'll come back to how to interpret that score. Now, we call this a linear classifier because the output is a linear combination of the inputs. That's a fancy word for saying it's a weighted sum with coefficients. Now, again, we'll come back to how to learn these weights from data next time. So we're just going to assume for today I have these weights given to me. But now I add these up and get a score for the sentence, and now let's explore what I might do with a score. So here's what I claim we can do. In our linear classifier, we get this weighted score, and then we use that score to make a prediction about the positivity or negativity of the sentence. And if you set up your scores just right, what you might do is say, hey, a score that's positive let's associate with a positive label. And if the score is negative, associate that with a negative label. So we learn our weights so that 0 is neutral, positive numbers are positive, and negative numbers are negative. So in that last example, where I had score of xi equal to 2.1, then using this rule, I would then predict the output for yi to be +1. And that's because it had more positive words weighted by their weight according to that table than negative words weighted by their weight in that. Again, I haven't talked about how to learn those weights. We'll get back to that. We're just going to pretend we have them. Okay. So I want to talk a little bit about notation for this. So the way that we're going to be describing this is that this model is taking the score function, where the score function is the weighted sum that we computed before. So it's coefficient 0 times feature 0 plus coefficient 1 times feature 1, and so on and so on. Now, what's kind of tricky in this setup for this model when we're working with text data is that each feature, h1 of x, might be something like the number of times good is in x. And then maybe h2 of x is the number of times great is in x. Okay. So on and so on. So we have one feature for all of the words we're going to need coefficients for. And then the score is just the weighted average of the number of times that word appeared times its coefficient from our score table. We add all of these up. So we call that the score of the sentence. And then the way our model is going to be set up at first is if that score is positive, we want to predict positive. And if the score is negative, we're going to predict negative. And we kind of represent this with this thing called a sign function. It's a function that takes a number and returns whether it's positive or negative. So for example, the sign of 0.8 plus 1, or positive 1, and the sign of negative 1,234,567,989. I don't know. That's going to be equal to negative 1. No matter how large the number is, if it's negative, the sign of it is negative. Okay? Those are our two things. The scores are these weights that we don't know how to learn yet. We'll come up with an algorithm to learn them. But we're going to have a feature per distinct word that we care about is either positive or negative. So you can imagine for text data, the number of features we'll be working with is quite large. And that's one of the big challenges of working with text data, but doesn't have to necessarily have anything to do with classification. We're going to be using a small number of words for examples, but classification is much more general than that. It's just any features, you learn your coefficients, and then you weight them. And just as a reminder, we'll sometimes use more convenient notation for this, where you might use a summation term to weight these up, or we'll use that super compact W transpose H to talk about vector multiplication. And again, you don't need to understand where that terminology comes from or that notation comes from. If you haven't taken a linear algebra course before, it's fine. You don't need to understand where it's derived from. But you just need to know when you see that, what we really mean is this sum of products like this. It's just a shorthand to describe that, so we don't have to write out that sum every single time. So that means we'll use this notation that the score of xi is going to be this W transpose H of xi. And we will commonly refer to this as S hat of I, our estimate of the score. And then Y hat, our predicted label, is the sign of S hat. It will just be helpful for us to give a name to the score or a variable for the score. We'll call it S or hat S because it's an estimate. But then we can talk about things in terms of their scores or their signs. So to be clear, each score is going to be a number between negative infinity and infinity. I actually will use that notation here. This means it's an element of this set. So each score will be a number, but the labels we predict, the Y hats, are going to be an element of the set -1, 1. So the output labels are either going to be +1 or -1, but the scores we use in our prediction might be any real number between -infinity and infinity. Okay? And this is just describing notation for this setup I had earlier, where I made a score, and then I made a prediction if that score was positive or negative. Now I'm just using notation to describe all of these things. S is for the score. The score function is the weighted average. Each feature corresponds to a word in this example. The coefficients we somehow learned from some ML algorithm. Once we compute the score, we feed it into the sign function, which tells us whether it's positive or negative. We're almost going to be wrapping up for today, but I want to show a bit of a visualization of what this is doing, and then we'll pick up where this leaves off in class. So what I want us to think about is what we'd call the decision boundary. And what I mean by this is trying to visualize the space of possible sentences and trying to find where the prediction between positive and negative changes. So here I have an example of a bunch of sentences. Each sentence in its feature representation is going to be simply the number of awesome or the number of times awesome appears and the number of times awful appears. So we're just going to reduce our feature space down to just 2 features, number of awesomes, number of awfuls. Just for visualization, all of this discussion extends quite naturally to when you have hundreds or thousands of features. So we're going to consider a simplified model that just looks at number awesome, number awful. And suppose I've already learned weights using an ML algorithm we'll talk about on Wednesday. So that means the score for any prediction will be 1 times the number of awesome minus 1.5 times the number of awful. Again, these are 1 and 1.5 are things that we learned from an algorithm. So what would happen if you had, say, 1 awesome and 2 awfuls? Oh, sorry. Actually, in my example, I want to use 5 awesomes and 2 awfuls. Well, in that case, your score would be 1 times 5 minus 1.5 times 2, which in this case would be 2 overall. And we'd probably predict positive for that, right? It's greater than 0. Sign of that is +1. So we report that. So now I want to look at kind of what happens to the space of all of these possible sentences. If we made a prediction for every single one, what would happen here? How would we figure out what these predictions are doing? So you can visualize this line, 1 times number of awesome minus 1.5 times number of awful, and consider all of the inputs of number awesome, number awful, that make this equal to 0, which is this kind of set of kind of combinations of awesome, awful that have a score of exactly 0. This is what we call our decision boundary, where when it's 0, this is when the decision's flipping between negative and positive. And so all of the things on one side of this line are positive predictions, and everything on the other side of this line is negative predictions. So this line right here, the line right here corresponds to score of x being equal to 0. This blue region down here corresponds to score of x being greater than 0, which means our prediction would be +1. And our region up here is where the score of x is less than 0, which we would predict as -1. And this kind of makes sense. In this region above the line, there are more awfuls than awesomes. And the points below the line, there are more awesomes than awfuls. Now, to be clear, it's not just about the raw number, it's about the weights, because awfuls contribute negative 1.5 each time, while awesomes only contribute positive 1. So it's about where the score balances out to 0. So things above that are more awful, things below that are more awesome. Now, another way of trying to visualize this, before I move on to the next slide, what I would then do is I would say all of these sentences with negative scores get predicted negative, and all these sentences with positive scores get predicted positive. That's my prediction rule. I look at if your score is positive or negative, and then predict +1 or -1 accordingly. To give you one last intuition about what this is doing, is the reason that this is kind of drawing a line with colors is we're really trying to represent a 3-dimensional function here. This function has 2 inputs and an output. The output is a score. It's a real number between negative infinity and infinity. If you had 200 awfuls in your sentence, it would be very, very negative. And no awesomes would be very, very negative. And so I've kind of tried to draw here on this slide this kind of gray slice right here. Oh, there it goes. This kind of gray slide right here is the picture we were looking at before, but it's like a side view now rather than a top-down view. And this plane is where score is equal to 0. And this function, 1 times awesome minus 1.5 times awful, defines a plane that says for any given awesome-awful pair, what's the score? And we are looking at all of the ones that have positive score being labeled as positive, and all the negative ones being labeled as negative. And what I'm doing in this picture on the left-hand side, the picture I've done before, is I've just collapsed this down in a top-down view, where I just labeled all of the points in blue that had positive score and all the points in yellow or orange with a negative score. So generally, with classification, we don't use plots like this 3D view because it's really hard to visualize and understand. Usually we'll use colored plots on the left-hand side to understand degrees of positivity or negativity. And just one other way of trying to visualize this score that we'll use quite frequently is sometimes we'll use the hue or intensity of the color to show if it's more positive or more negative. And so commonly you'll see examples like this, where instead of just using blue, orange, I'll use blue on a gradient to orange, where white is the score near 0. It's a very neutral color. So it's very, when we're talking about the score being 0, we'll label it as white. And then the lighter the color, the closer to 0 it is. And then the darker the color, either blue or orange, means more positivity or more negativity. And that is kind of where I want to leave us off today. In class, we're going to pick up where this leaves off and discuss how we can think about what this decision boundary is doing, and then talk a little bit more about how to evaluate these models, determine whether they're making predictions we want, or determine how good the predictions that we're learning. I want to remind you that we're not going to talk about how to learn the weights yet. We're going to talk about that on Wednesday. So today in class, we're really going to be talking a lot about evaluation and thinking about what these decision boundaries are doing.